Okay, thank you very much. First of all, I would like to thank the organizers to give me the possibility to speak here, especially because this year's spring lecture series topic nicely fits what I wanted to tell you today. So I will present you some quite old problem in differential geometry, which I translate to a completely algebraic problem stated in terms of representation theory. And then I will solve this problem using representation theory. And then we will see some nice implications of the solution on the initial problem. So what's the problem? Well, in general, if you have a partial differential equation, it's natural to ask in which coordinates does this equation allow a solution by a separation of variables, and to classify these coordinate systems. So here in this talk, I will focus on the Hamilton-Jacobi equation. So to address this problem on an arbitrary Riemannian manifold, the main tool is integrable killing tensors. So for me, a killing tensor is just a symmetric 2 tensor, which satisfies the generalized killing equation. And integrable means that locally you find coordinates such that if you raise one index, so you get an endomorphism, then the coordinate vectors are eigenvectors of this endomorphism. So then we have this nice result that every coordinate system, every orthogonal coordinate system in which the Hamilton-Jacobi equation separates, gives rise to such an integrable killing tensor with some additional conditions, pointwise simple eigenvalues, and a certain compatibility with a potential, and vice versa. Each such tensor gives a coordinate system in which the Hamilton-Jacobi equation separates. So a first step to solve this problem would be to determine integrable killing tensors. So the definition I gave you is not very appropriate to tackle this problem. That's why we use a different characterization of integrability, which is a quite complicated system of partial differential equations involving the Nyhenhaus torsion of the killing tensor. So we can restate our problem and say that we want to solve this system of partial differential equations in a particular case, S3, or the 3-sphere. Okay, how does this translate to algebra? For this, we need the notion of algebraic curvature tensors. This is nothing else than a tensor, a 4 tensor on a vector space, satisfying the usual symmetries of the Riemann tensor. And of course, from the perspective of representation theory, this is nothing else than a representation, an irreducible representation of the general linear group. We have seen this already today, and it corresponds to this 2x2 Young diagram. Okay, now if we regard the isometric embedding of the sphere into a Euclidean vector space, then the isometry group is just the orthogonal group, which is a subgroup of the general linear group of the ambient space. And we have this correspondence found by McLennan and Milson and Smirnov, which says that we have a bijective correspondence between killing tensors on the sphere on one hand and algebraic curvature tensors on the ambient space on the other hand. And this is given by this simple polynomial expression. By the way, this holds in general for constant curvature manifolds. So now having a completely algebraic description of killing tensors, it's clear that any condition, such as integrability, must be expressible purely algebraic. The only question is, how difficult is this? And the answer is that it's surprisingly simple. Particularly, we have this result that a killing tensor on the sphere is integrable if and only if the corresponding curvature tensors satisfies 2 algebraic equations. The first one, for example, just states that a particular irreducible component of a quadratic polynomial in the algebraic curvature tensor vanishes. And similarly for the second one. And the same formula holds for constant curvature, arbitrary constant curvature manifolds. Okay, why is this better than the initial system? Well, first of all, it's algebraic equations. So we have replaced a system of partial differential equations by purely algebraic equations. You might have observed that the algebraic equations, there was a third equation missing. And in fact, in the constant curvature case, we can prove algebraically that the third one is a consequence of the first two. So the system is simpler. Then this approach is completely generic for constant curvature manifolds. And of course, it uses curvature tensors. Curvature tensors are one of the most studied objects in differential geometry. In particular, quite a lot is known about the algebraic properties of curvature tensors. And finally, the most important fact is that formulating the same problem but in a different theory, algebraically in this case, gives us new insight into the problem from different perspectives, from representation theory, from algebraic geometry, and if you consider the problem modulo the action of the isometry group, then you end up with a problem of geometric invariant theory. So to make this more explicit, let me tell you something about the solution on the three-sphere. So first, on the three-sphere. Three-sphere corresponds to an ambient space of dimension 4. And rising two indices of the curvature tensor, we can regard it as an endomorphism on two forms. So in dimension 4, this is a 6x6 matrix. And the first...
Sorry, I meant to ask this before, but now, when you write down your modules, are you writing down GL modules or SL modules?
GL.
So everything is...
Yes, this is surprising. Yeah.
And then can you go back one slide, please, for a second?
This one?
Well, actually, I guess it's like way back. Everyone, just keep going. Okay, yeah.
Okay. So for the three-sphere, the corresponding curvature tensor is a 6x6 matrix, and we have this nice result. If the Keeling tensor is integrable, then the corresponding curvature tensor in an appropriate orthogonal basis is diagonal. And moreover, integrability of such a diagonal tensor can be characterized by the vanishing of a certain determinant, which is linear in the components of the curvature tensor. This means that algebraically, this integrability can be described by a linear determinantal variety. And this is a cubic form in P4.
Sorry, your result, though, for the condition was on S3 or SN?
S3.
Okay.
I will say some words on SN later on. Okay. Let me tell you something about particular solutions from the different perspectives. So,
but if we're on S3, S22 is just sim 2.
Hmm?
If we're on S3, S22, the square box is just the same as 2 boxes. 4 boxes is the same as 2 in S3. He went up to the S3. He did go up.
I don't understand.
No, but that's the curvature tensor.
The curvature tensor lives in one dimension higher.
Ah, okay.
It's the curvature tensor of the ambient space.
No.
It's an algebraic curvature tensor.
Right.
Okay. So, well, we know that quite wide family of integrable Keeling tensors arises from geodesically equivalent metrics. I call these Keeling tensors Benanti Keeling tensors. And there's a nice representation theoretic interpretation of this construction, which is the Kulkarni-Nomizu square. This is the natural way to construct a Riemann tensor out of a symmetric 2 tensor, which is just taking the symmetric product decomposing into irreducible components and projecting down to the component corresponding to curvature tensors. On the algebraic geometric side, this corresponds to a projection of the Veronese variety, which is a subvariety of P5, smoothly down to P4. So we find this Veronese variety on our variety describing integrability. And on the other hand, from the algebraic description, we easily see that curvature tensors with vanishing Weyl component are in fact integrable. I call them Ricci-killing tensors. And from a representation theoretic argument, you see that these must be isomorphic to special conformal killing tensors on the sphere. And from the perspective of algebraic geometry, this is just a projective plane on our variety. So I haven't told you about the exact correspondence between integrable killing tensors and separable coordinate systems. This is given by so-called Stekel systems, which are vector spaces of dimension n containing commuting integrable killing tensors. So what does this mean in our case? This means that Stekel systems and thereby separable coordinate systems correspond to projective lines on our variety. And stated in another way, this means that separable coordinate systems constitute a subvariety of the Fano variety of our variety. The Fano variety is a variety of projective lines. And since our variety is a linear determinantal variety, these Fano varieties are quite well understood, at least for 3x3 matrices, which is the case here.
Sorry, what's the script V
The
then?
V is the variety describing integrable diagonal curvature tensors. So you get every curvature tensor out of V by applying an orthogonal transformation. So, and then we have this characterization of Stekel systems or separable coordinates. First of all, we encounter in every Stekel system a unique Ricci-killing tensor and also a unique Benanti-killing tensor. And both of them, at least generically, span the Stekel system. So we have canonical representatives. And for one of them, for the Benanti-killing tensors, it's quite simple to solve the eigenproblem. And the eigenproblem, solving the eigenproblem is necessary to compute explicitly the separable coordinates. And what you obtain is the list of separable coordinates on the sphere, which has already been known for quite a long time. But I hope I convinced you that using this algebraic approach, you get much more insight into the geometry which is behind this problem. And the initial solution is just given by local coordinate computations, and you don't really see this nice geometry. And if you're not convinced, then let me tell you that the real potential of this algebraic approach is in all the possibilities to generalize this result. So you can apply the same technique to solve it for flat space. This is a bit more complicated because the isometry group is more complicated. Then you can try to solve this for negative curvature for hyperbolic space. And using spinors, at the end, this involves the Petrov classification for Riemannian curvature tensors. This is joint work with Robert Milson from Halifax. Then, of course, is the question you posed, what happens in higher dimensions? In fact, from the construction of these coordinate systems in higher dimensions, this suggests that on the sphere, this holds true in general that to integrable killing tensors correspond diagonalizable algebraic curvature tensors. But this is still a conjecture, and we hope to find some iterative construction process for coordinate systems in higher dimensions, separable coordinate systems. And of course, the most interesting question is what happens in non-constant curvature. You can do this on a case-by-case procedure. The first candidate would be a CPN because it's not too different from the sphere. And we would also like to understand this in terms of BGG theory. This is joint work with Andreas Chapp and Matthias Hammerl. And of course, one can consider different equations. In fact, there are characterization of separable coordinates for the Laplace equation and for the Eikonal equation and other equations, which all somehow involve Killing tensors or conformal Killing tensors and some conditions on them. So the hope is that this is quite a general approach. Well, in general, I believe that from this interplay between geometry on one hand and representation theory on the other hand, we can get much more information out of this type of problems. So, okay, that's all I wanted to tell you.
Could you say what those quadratic and cubic equations are as modules of equations?
As modules of equations?
Yes, they're modules.
No.
Yeah, so we had a little interchange here, and I want to make sure I understood right. So I was thinking that you were saying that for S3, that the curvature tensors would be on a 5-dimensional vector space?
No, on 4-dimensional vector space. It's Killing tensors. It's not conformal Killing tensors. It's projective Killing equation. It's not the conformal Killing equation.
Oh, I see.
Yes.